Let's continue our discussion on data encryption by talking about modes of operation. Now, a mode of operation is simply a means of using a cipher within a product to achieve a security goal such as confidentiality or integrity. Now, there are many types of modes of operation. Digital signatures are one of them. Now, public key cryptography can authenticate a sender, while hashing can be used to prove integrity. So you can actually combine both to not only authenticate the sender of the message, but also prove the integrity of that message. And this combination is what we call a digital signature. Here's an example of how this would work. Alice will first of all encrypt her message using her own private key. And she's also going to encrypt that message with a digital signature. She's going to send that message with the signature and public key to Bob. Bob will then decrypt the signature using Alice's public key and will get the reference hash value. Bob will then compute a hash value of his own and compare it to the reference value to make sure that the file has indeed not been tampered with. So in this kind of scenario right now, because the hash values are going to be the same, this will prove the integrity of that file, and because Alice used her own private key which she only has access to, it's also been authenticated that indeed the message came from Alice directly. So a digital signature is a hash that is encrypted using a private key. Without this encryption, another party like Mallory or a hacker could intercept and modify the file, thus computing an entirely different hash and sending that modified file and hash to the recipient. Now, it is worth mentioning that the recipient must have some means of validating that the public key really was issued by Alice. Keep that in mind. Now, digital signatures do not provide confidentiality. It's very, very important for you to understand this. They can provide integrity and authentication, but cannot provide confidentiality. Now, there is something known as the digital signature algorithm, the DSA. This typically uses the elliptic curve cryptography rather than the RSA cipher to achieve similar goals. We also have digital envelopes and key exchange. Here, symmetric encryption can encrypt and decrypt large amounts of data because it's very, very, very fast, but it is difficult to distribute the secret key securely. So we have something known as the asymmetric PKC encryption. This can distribute the key easily, but cannot be used for large amounts of data. Remember when we talked about both symmetric and asymmetric? Symmetric is fast, can be used to encrypt large amounts of data, but it's not very, very secure. Asymmetric is very, very, very secure, but cannot be used for encrypting large amounts of data. So what happens here is that you can combine both in the same product in a type of key exchange known as the digital envelope or hybrid encryption. Here, the sender and recipient can exchange a symmetric encryption key securely, but by using the public key cryptography. That's how this would work. So here's an example. Alice would obtain the copy of Bob's public key first of all. She will then encrypt the file using a symmetric key. She then encrypts the symmetric key using Bob's public key. That's the key here, all right? And then number 4, Alice will then send the ciphertext and encrypted symmetric key to Bob. Bob will then simply decrypt that symmetric key using his own private key, and then Bob decrypts the ciphertext using the symmetric key. It's a little bit complicated, but if you spend some time to actually go through the process, you would understand it easily. Also, keep in mind that it is the recipient's public key that is used for the encryption, while the recipient's private key is going to be used for decryption. Also, the private key must be kept secure and available only to the authorized user. That's very, very, very important. We've got digital certificates, another mode of operation. Now, public keys are used and are freely available, but how can anyone trust the identity of the person or server issuing that public key? That's the thing. Public keys, they're always available, but how do we know that this public key actually came from Alice or the authorized person. So here, a third party known as a certificate authority, a CA, can validate the owner of the public key by issuing the subject with a certificate. So the process of issuing and verifying certificates is known as the public key infrastructure, the PKI. Now, we also have something known as the perfect forward secrecy. See, when you're using a digital envelope, if data from a session was recorded and then later in the future, that server's private key got compromised, it could be used to decrypt the session key and recover the entire confidential session data. So how do we combat this? This risk is mitigated by the perfect forward secrecy. Now, how does this work? Basically, the PFS uses the Diffie-Hellman key agreement to create something known as an ephemeral session key without using the server's private key. Now, ephemeral keys are those used within the context of a single session only. So rather than having the key run through the entire communication between the sender and the recipient, we can use ephemeral keys that would work with just one single session only. So the DH, the Diffie-Hellman, allows both parties to derive the same shared secret just by agreeing some values that are all related by some trapdoor function. Now, in the agreement process, they share some of them, but keep others private. That's how the perfect forward secrecy works. Now, here's an example. This is a bit complicated and involves some mathematical calculations. I'm going to leave this for you to go through. It's a bit complicated, but you can spend some time to go through the entire process and do some calculations on your own just to show you how the PFS would work. But the most important thing to remember is that PFS simply uses ephemeral keys, and ephemeral keys are those that work within the context of a single session only. That's what you need to know for the exam. Now, using ephemeral session keys also means that any future compromise of the server will not translate into an attack on recorded data. So even if the attacker can obtain the key for one session, the other sessions will remain confidential because, again, ephemeral keys are used for single sessions only. Now, the PFS, the perfect forward secrecy, can be implemented using either Diffie-Hellman, ephemeral mode, the DHE, or the EDH, or the elliptic curve Diffie-Hellman ephemeral mode, the ECDHE algorithms. Thank you for watching. I'm going to see you in the next class.